Hi there, and welcome to our lecture on behavior of gases. We're in States 4 of Unit 2. Our key ideas: what are some properties of gases? How can you predict the effects of pressure, temperature, and volume changes on gases? This lecture, you'll want to definitely pay attention to being able to differentiate between these three variables. Alright, so first key point that we're looking at here: gases will expand to fill their containers. They spread out easily, they mix with one another, they've got low densities, and they are compressible. Unlike solids and liquids, gases are mostly empty space. Also, gases will exert pressure on their containers. Got some video clips here. Let's see what they've got to say.
Gases differ from solids and liquids in that they expand to fill the shape of their container. Because there are large distances between gas molecules, gases have extremely low densities. Carbon dioxide, for example, is less dense than water, so bubbles of carbon dioxide rise to the surface. Gases are compressible to small fractions of their initial volumes. Because of this, large amounts of oxygen can be stored in tanks for scuba diving. Gases mix readily by diffusion. We don't have to stir or shake them to make them mix. Gases can escape containers through tiny holes in a process called effusion. This occurs when a bicycle tire is punctured.
So how can we predict the effects of pressure, temperature, and volume changes on gases? So we do have several gas laws that we're going to be looking at here. So the gas laws will help us understand and predict the behaviors in specific situations. So we can define gas laws as the laws that state the mathematical relationships between the volume, temperature, pressure, and quantity of a gas. Starting with Boyles Law, this relates pressure of gas to its volume. So Boyles Law, for a fixed amount of a gas at a constant temperature, so we're not going to change the temperature for Boyles Law, and we're not going to change how much of that gas we have. The volume of the gas increases as the gas's pressure decreases. Likewise, the inverse is true as well. The volume of a gas will decrease as the gas's pressure increases. So we can express this mathematically. P1 times V1 equals P2 times V2, where P is pressure, V is volume.
Pressure is caused by the collisions of gas particles with the side of the container. With a large volume, the particles do not collide with the sides of the container very often, and the pressure is relatively low. When the volume decreases, the particles of the gas collide with the sides of the container more often. With more collisions, the pressure increases. Boyles' law states that the volume of a fixed mass of gas varies inversely with pressure at constant temperature. In other words, the smaller the volume, the higher the pressure.
Alright, so some math skills related to Boyles' law. So we've got a situation: the gas in a balloon has a volume of 7.5 liters at 100 kilopascals. The balloon is released into the atmosphere, and the gas expands to a volume of 11 liters. Assuming a constant temperature, what is the pressure on the balloon at the new volume? So we're going to list the given and unknown values. So V1 is 7.5 liters. Our initial pressure is 100 kilopascals. And our second volume, or what the volume changes to, is 11 liters. So our unknown is going to be our second pressure. What's that pressure now at this new altitude, new atmosphere? Because the relationship V1 to P1 is equal to V2 P2, we should be able to logically think this through, but let's go ahead and finish the math. So we're going to write the equation. So we're going to rearrange that initial equation that we had, that P1 V1 times P2 V2, and we're going to rearrange it so P2 is by itself, because that's what we want to solve for. We're going to plug those numbers in. So we're going to multiply the top set of numbers, divide by the bottom set, or the bottom number, sorry, and it's going to give us 68 kilopascals. So this should make sense then, that at a higher pressure we had a lower volume. When there was less pressure being applied to the balloon, the volume got larger, or we directly observed the balloon getting larger. So that should take us to logically feel or logically express that there's not as much pressure pressing down that balloon, so it's able to get larger. Our next law is Gay-Lussac's law. This relates gas pressure to temperature. So now we're looking at pressure versus temperature. So to define Gay-Lussac's, the pressure of a gas increases as the temperature increases. If the volume of a gas does not change, and then the pressure decreases as the temperature decreases. So we're going to keep volume constant with Gay-Lussac's law, but the pressure and temperature is going to be changing. And then our third relationship, is Charles' law, and this is looking at temperature with volume. So with Charles' law, for a fixed amount of a gas at a constant pressure, the volume of the gas increases as the gas's temperature increases. Likewise, the volume of the gas decreases as the gas's temperature decreases.
Charles's law states that the volume of a fixed mass of gas at constant pressure varies directly with Kelvin temperature. Liquid nitrogen is very cold, at 78 kelvins. When a balloon is placed in liquid nitrogen, the balloon shrinks. As the temperature decreases, the volume also decreases. When the balloon is removed from liquid nitrogen, the balloon returns to its original volume, as the air warms the balloon to its original temperature.
What I want to try in this video is a few review questions, just to kind of make sure we got it down. So the gas in the cylinder of an automatic engine undergoes change shown below. Here we go. And what happens to the pressure of the gas? So here we're going through this change, so the volume is decreasing. So what's happening to the pressure? So as the volume decreases, the amount that these particles are hitting the side of this container increases. Okay. The gas in a toy balloon expands outward as shown below. After the expansion, what happens to pressure? So we have a small balloon. We're not changing the particles within the balloon. It expands. Because it's expanding, we should expect that our pressure within the balloon is decreasing. There it goes. Decreasing, pressure decreases. Alright, the temperature of water vapor in a pressure cooker increases. What happens to the pressure of the gas? So temperature is increasing, so our pressure should be increasing as well. So, thanks for listening.